Hello everyone, I'm Zhihan, and I'm excited to present our work. In ebony, high-quality in-the-wild imaging from extreme degraded nanophotonic bursts, our results show that despite their extreme optical limitations, ultra-thin nano-optical Metalens cameras can still deliver high-quality HDR imaging in real outdoor handheld use. The key idea is to co-design nano-optics and burst restoration in an end-to-end system. Traditional imaging systems rely on static refractive glass elements to correct optical aberrations. This stacking fundamentally limits how thin a camera can be. Metalens instead use sub-wavelength nanostructures to manipulate the optical wavefront. They are orders of magnitude thinner than conventional optics, over 10,000 times thinner. This makes them extremely attractive for compact cameras, wearable devices, and edge systems. However, this extreme thinness introduces severe imaging challenges. Metalens suffer from strong chromatic aberrations, broadband blur, manufacturing-induced distortions, and reduced signal-to-noise ratio. In real-in-the-wild sense, this degradation compound. As shown here, the captured frames are heavily blurred and distorted. This level of blur makes alignment and HDR fusion extremely difficult. The question becomes, can we make such extreme degraded bursts usable for real-world HDR imaging? To address this challenge, we design an end-to-end system. We jointly optimize Metalens optical design and a burst HDR restoration framework. Instead of treating optics and computation separately, we co-design them to work together. We also built a handheld prototype system for real-in-the-wild validation. First, we optimize the Metalens using differentiable wave propagation. We jointly optimize the focal spot reduce across broadband wavelengths from 400 to 700 nanometers and pixel-level reconstruction noise over target images. This enables improved broadband focusing behavior and produce a PSF that is more favorable for computational restoration. Importantly, this reduces downstream restoration burden. After capturing exposure-varying bursts, we produce them through our HDR pipeline. We first select a reference frame, then we perform burst alignment under extreme blur. The aligned frames are passed into a weighted burst fusion stage to better handle dynamic range in consistency. We introduce an adaptive pixel correction unit, or APCU. Finally, a lightweight unit predicts a residual image. The final HDR output is obtained by combining initial estimate and learned residual. Let's zoom into two key components. On the left, we show our UNet backbone. It's composed of lightweight nav blocks, enhanced with attention fusion blocks. We also introduce scale and shift feature transforms to adaptively modulate features. On the right, we illustrate the weighted burst fusion module. Instead of naive averaging, we learn per frame confidence weights. These weights are normalized via softmax and used to fuse aligned frames. This allows the network to selectively emphasize reliable regions. Burst alignment is particularly challenging in our setting. Unlike standard burst photography, our frames are severely blurred and lack strong high-frequency features. Traditional feature matching often fails. To address this, we introduced a blur-aware multi-scale alignment strategy. We enhanced features from fine to coarse scales and refined patch-wise transformations. This enables reliable alignment even under extreme degradations. Accurate alignment is critical, otherwise HDR fusion would produce a ghosting artifacts. A major challenge in HDR reconstruction is handling saturated regions. In high dynamic range sense, certain pixels are clipped and unreliable. We introduced a saturation-aware fusion mechanism. Specifically, we dedicate saturated regions and downweight them during burst fusion. This prevents highlight artifacts and improves stability in outdoor sense. When deploying outdoors, we observe a dynamic range distribution shift compared to laboratory training conditions. In particular, saturated regions are misweighted. We introduce a saturation-guided regularization to stabilize fusion map under extreme illumination. This enables robust in-the-wild HDR reconstruction. Let me first show qualitative results on the real in-the-wild HDR sense. On the left, you see the robust captures from the Metalens camera. Due to the extreme blur and chromatic distortions, fine structures are barely visible. Baseline methods struggle to remove the broadband blur and often produce color artifacts. HDR train improves dynamic range but still suffer from residual blur and ringing. In contrast, our method restores sharper edge, more natural colors, and better highlight details. The reconstructed results are significantly closer to reference images. Beyond visual quality, we also evaluate speed and computational efficiency. On the left, we compare reconstruction quality versus throughput. Our method achieves higher PSNR while maintaining interactive frame rates. On the right, we show quality versus computation costs. Compared to both burst and non-burst methods, our approach achieves superior reconstruction quality with competitive computational complexity. Importantly, this enables practical development on edge devices. To summarize, we co-design Metalens optics and burst learning. We introduce blur, robust alignment, and saturation-aware HDR fusion. We address dynamic range shift for in-the-wild development. We demonstrate high-quality HDR imaging from extreme degraded nanophotonic bursts. This work brings ultra-thin nano-optical cameras closer to real-world development in mobile and edge devices. Thank you for your attention.